Okay, this video is going to go over a lot of the some of the common applications that we use for vectors, and you'll see some things that might be familiar to you if you've taken physics. For example, here we have a classic type of problem where we've got a car on a hill, and we want to know how much braking force is required to keep this car from rolling down the hill. Well, there's some things that are important to understand about this, and one of them is that gravity acts kind of perpendicular to, it does not act necessarily perpendicular to the surface of the Earth, because if you're on a hill, gravity's always going to pull you towards the center of the Earth. So if we say like this car here is getting pulled straight down by gravity, then you can see that there's only some component of that force is going to be in the direction of the hill. So in parallel with the surface of the hill. The other is going to be perpendicular with the hill. And so that's what we're going to end up doing here. But we have this car, it's 5,267 pounds, and it's sitting on a hill with a 22-degree slope. We want to know what force do the car's brakes need to apply. Okay, so we want to answer to two questions. What's the force perpendicular to the hill? That's something called a normal force. And we want to know what is the braking force. Okay, so uh, first of all, there's 5,267 pounds going down. Okay, definitely that is what's happening. Now we also have this hill here. Okay, so this is the hill, and there is a braking force that's going to need to be applied effectively in this direction to keep the car from rolling down the hill. And so in order to find this force, we need to find what's the force that's causing this car to roll down the hill. Obviously, it's because the car weighs something and it's on a hill, and if you put something on a hill and it rolls, it's going to go down the hill. So you have to counter that force. It's going to be the exact opposite of that force. So how do we figure out what that is? Well, what we do is we break this force down into two components. We break it down into a force that is perpendicular with the surface that it's on, and we break it, and then we also have the force that is the vector component that is parallel with the ground. So what we need to do, right? The answer to what is the braking force is the green vector, and the answer to what is the orange, what is the normal force, the perpendicular to the hill force, that's the orange there. Now, the key then, and we should be able to do this if and only if we know what this angle theta is. Okay, because if we do, well, we have the hypotenuse, it's 5,267. And if we have an angle and a hypotenuse, we can find the other two sides. So, the only angle given to us in this problem is 22 degrees. Now, it kind of should be a little bit of a giveaway that that is indeed the angle here, but let's see why that's the angle. And the key here is because, well, let's actually extend this triangle out a little bit more. Okay, I'm drawing all over the place here. But if we look at this big triangle, I'm going to do this big triangle in light blue. Okay, this triangle right here goes over there and comes this way. Okay, it's a right triangle. On that angle right there is 90 degrees. This is 22 degrees, and we know it's 90 degrees because we specifically drew that orange vector perpendicular to the surface. So we know that that's 22 degrees, that's 90 degrees. That means that this angle right here is all the angles inside of a triangle add up to 180 degrees. So if one of them is 90, one of them is 22, the other one must be 68 degrees. This has to be 68 degrees. Okay, then I'm looking at this small triangle here, right, where it involves theta, the theta I need. Well, boom, right there, that's 90 degrees. So if that's 68, that's 90, then this is 22. So we have similar triangles here. They're both 22, 68, 90 triangles. So with that being said, we have this triangle here. So this is all messy now. Let me just freshly draw back over it. We have that original force of 5,267. Okay. We have this this perpendicular force we want, and then we have this braking force. So to find the braking force, okay, braking force, it is going to be, now we're kind of, you got to think about what the perspective is here. We have this angle theta. So with respect to that, with respect to that angle theta, we want to know this opposite side. We have the hypotenuse. So the opposite force for this would be equal to 5,267 times the sine of 22 degrees. Okay, and conversely, like we want to know for the normal force here, okay, the normal force, or the force perpendicular to the hill, that would be the adjacent, right? That's this adjacent side with respect to that angle. So adjacent would be 5,267 times the cosine of 22 degrees. Now, I actually don't have those numbers handy. Let me do that really quickly. 5,267 times the sine of 22 degrees. I'm in degree mode. That is, this one is, we need 1,973 pounds-ish of braking force. And the other one, 5,267 times the cosine of 22 degrees, we've got 4,883.5-ish. 0.5-ish pounds of force acting perpendicular to the hill. So a person might need to know this if they're designing a car and they know how much it weighs. They may need to know like what materials or how big the brake calipers need to be, or how big the rotors need to be, what kind of calipers to use, all kinds of things like that. Okay, another kind of application here we have is work, and key to understanding work is that work is equal to force times distance. You can imagine if you're pulling something and you pull it like 10 feet, that is more work than if you pulled that same thing in the same way for 5 feet. It's twice as much work, right? So it's dependent on how far you pull something and the force you're using. Now, if you have this wagon, or what is it? Sorry, a laundry basket. Okay, so we got a laundry basket. It's full of clothes. And it's being pulled at an angle of 42 degrees with the horizontal. So the force that this is being pulled at, oops, I gotta draw the clothes back in. The force that this is being pulled at is 42 degrees with the horizontal. Now, if you think about the components of this force here, okay, we have a horizontal component and a vertical component. Only the horizontal component is applying force in the direction that we're trying to go. So only the horizontal component of this force is doing any work. The vertical component is not insignificant, right? If you consider all sorts of things like friction and stuff, there's benefits to that that vertical force, but the horizontal force is the one doing the work in the direction. It's sliding along the ground in that direction. So we need to know then what is, so that this force is actually the force in the x direction. So we need to know what is this force right here. Well, from the previous examples, it should be pretty clear. This is 23 newtons being pulled here. So we know then that this would be 23 times the cosine of 42 degrees. And if it's going 16 meters, all we need to do is say 23 times the cosine of 42 degrees. That's the number, that's the amount of newtons that's being exerted in that direction, then times the distance of 16 meters. And that is the amount of work being done by Jake as he pulls his laundry basket full of neon clothes. So the answer to this is 23 times the cosine of 42 degrees times 16, which is 273.5-ish. And the unit for work is joules. Okay, the unit for work in metric and standard units is joules. Joules are kilogram Newton per meters. So kilogram is Newton meters, right? Newtons times meters, and then newtons are kilogram meters per second squared, right? So joule is a kilogram meter squared per second squared. Anyway, that's not super important, but that is how you would compute work. Okay, now by far the most difficult application for vectors that we're going to cover in this class is the quote-unquote airplane problems. And kind of key to understanding why these are difficult is that there's some vocabulary that's kind of strange. before I talk about that vocabulary specifically, if you've ever been in like an airport that has a moving walkway, or if you've been even on an escalator in a mall or in a hotel or something, you know that, like, for example, on the moving walkway, if you're walking at your normal walking speed on that moving walkway, you're actually traveling much faster, right? Because your actual speed relative to like a fixed point is greater. It's the combination of the moving walkway speed plus your own speed, okay? Plus what your normal speed would be just on solid ground. Same thing for escalators. If you're walking up an escalator, like if you're climbing the stairs of the escalator as it's moving, you're climbing up, you're gaining like height much faster than you would if you were just going upstairs by yourself. Um, and so those are the kind of things that we're talking about when it comes to these two terms of airspeed versus ground speed of an airplane. There's like the actual speed, the actual speed relative to a fixed point is what your real speed is, right? But then there's like an airspeed, which is like, let's say you're a pilot and you push the dials and move the levers and you tell, your airplane to go, I want you to go 400 miles per hour. Well, if there's a wind pushing you forward an extra 100 miles per hour, your actual speed, which would be called a ground speed, is 500 miles per hour. And so those are the two important things to know. Is like is what's your actual speed that you set, and what is your actual relative speed relative to a fixed point on the ground. The other thing that's confusing about navigation problems in general, so airplanes are things that are navigated, is that when we discuss angles, we talk about them in terms of what are known as headings. And headings are angles that we cite based off of true north. So, for example, if I was going off in this direction right here, and let's say that angle right there is 50 degrees. And we would know from math that, okay, it's a 50-degree angle in the standard position. Okay, what this sort of angle description tells us is that we don't want this angle here. We actually want the angle off of this vertical. So this here is it's not standard position, but this is my initial side, kind of, you can think of an angle. There's a terminal side over there. So what's this angle? Well, hopefully you can see that the conversion there is just a complement. So it's actually 40 degrees. So it's actually a 40-degree angle. And the way we describe it is as north, because we're in the quadrants, you can think of this as quadrants 1 and 2, it's north 40 degrees east. So we go north and then 40 degrees towards the east, and that's how we write it like that. Okay, if we, for example, had an angle down here, let's say from standard position this was 70 degrees, well then we would have an angle that is south. So we start with either north or south, and then we're 20 degrees, right? 20 degrees is a complement of 70 degrees. So this would be south 20 degrees west, because it's south and then it's heading 20 degrees towards the west. Let's do some practice there. Okay, so here's an angle given to you in standard position of 38 degrees. What is the equivalent heading? So that means, well, it's north, and then how many degrees is that towards the west, right? This is west. Well, it's going to be north, and then what is 90 minus 38? 90 minus 38 is, beep boop bop bop, is 52 degrees. 52 degrees west. Okay, here's another one, 71.35 degrees on a standard position. So this would be south some number of degrees east, right? South some number of degrees east. So the complement of 71.35 would be south, what's that? 18.65 degrees east. Okay, one last one. We have north 20.58 degrees east in the bearing, so that means that this angle right here is 20.58 degrees. What would be the standard position equivalent? Okay, so again, it's just complement. All we have to do is take 90 and subtract 20.58 degrees. That'll give us the complement. So this actually the standard angle here. This angle here would be 69.420 degrees. Okay, and really quickly here, this is just one basic problem that's similar to that takes into consideration these concepts, and then in the next video we'll do some actually really quite difficult ones. Um, we have a boat, okay, a boaty McBoatface. He's going across a river. Okay, here's the two sides of the river, and the river is in the middle here. Okay, we have Bodie. Let's say Bodie's red. Okay, here's Bodie, very happy. He's got a he does he's like a steam or a diesel powered boat or something, and he's trying to go to the other side of the river. Okay, the river's current is 10 miles per hour. So let's say the river's current is going this way at 10 miles per hour. All right, at what angle relative to directly across the river should Bodie steer to get directly across the river? So let's pretend there's like a dock over here, exactly opposite. If if Bodie's driver aimed towards the dock, you see that the river is going to push him down, right? The vector of the river's velocity is going to push him off course. So Bodie's going to have to aim somewhere up in this area. If he aims this area, then the river will have him push back down to where he wants to go. So let's formalize that actually. So we want Bodie's actual velocity vector. We want to set it to be that, so that the river then will come and push us down to where we want to go. And so you can see that there's a right triangle here. Okay, so we're dealing with this right triangle, and we know the magnitude of this opposite side is 10. It's 10 miles per hour, like south, right? Okay. What we want to know actually, we want to know at what angle and how fast would he have to go in order to get there. Okay, so we want to know this angle theta, and we want to know what this this speed, let's call this vector b. We want to know the magnitude of vector b. So we can do this because we also know that the distance here, the distance across the river is 50. Oh no, it's not. It's what do we know here? Oh, Bodie can go 50 miles per hour, right? So Bodie can go 50. How fast would Bodie actually be going? Yeah, so if we put this as, we know that this is 50. Hold on, let's see, what are we doing wrong here? This is 50, so we actually know Bodie. We want to know what his actual speed is going to be. We know that he can only go 50, right? So he's going to end up going like a little less than 50. So we want to know this magnitude. So let's say this is his actual speed A, and this is his actual what happens at the end. Okay, it's his like observed speed. Hopefully that made sense. That was a little confusing there, but what we're trying to find is this value here and this angle theta. So we can do that because we know, let's just draw this triangle. If we have two sides of a right triangle, we can definitely find a third. We can use Pythagorean theorem, okay, totally, or we could even do it another way. With respect to this angle theta, we have the opposite side and the hypotenuse. So that means the sine of angle theta is equal to 10 over 50, or just 1/5. So if you did inverse sine of 1/5, you would get what theta is equal to, and theta then would be equal to inverse sine of 1/5, which is 11.537 degrees. Okay, so that's the angle he would have to set off relative to directly across the river and standard position. And if we wanted to then know what this is, we can solve it. If we wanted to find the answer to how fast we would have to go, we could just use Pythagorean theorem there, right? So the b squared is equal to 10, b squared plus 10 squared, right, is equal to 50 squared. So b squared is equal to 50 squared minus 10 squared, which is going to be this. What is that? I don't know what that is off the top of my head. Let's do the math on that. So it's 2500 minus 100. So what's the square root of 2400? The square root of 2400 is 20 root 6, which is 48.99-ish, basically, miles per hour. So Bodie sets off across this river. He's the pilot, Bodie's driver, or let's say Bodie is autonomous. Bodie sets his own speed to 50 miles per hour, but he's heading upriver, right? He has to head upriver, so some component of this river's velocity is going to counteract his velocity across the river and make him slow down. So the answer then is he'd be going 48.99 miles per hour, which is 49 miles per hour, at 11.537 degrees, relative to directly across. Hopefully that made sense. Okay, so in the next video we'll get into some more complicated problems.